Differential equations, section 4.7. We're on our final day, day 3, where we're going to use undetermined coefficients, but we're really going to make a link using a substitution to be able to look at a problem that we've gotten very confident and comfortable with earlier in chapter 4. We're still going to be looking at Cauchy-Euler differential equations. We're going to be looking at non-homogeneous ones at that. One method that you may use is variation of parameters. That's using the Wronskian. You can find your characteristic solution, y sub c, in much the same way we've been doing all of chapter 4. And then divide by lead coefficients to make sure you have a 1 there, and then you can set up, as we had seen before, like a u1 prime would be w sub 1 over w. That's always going to be an option so that you can find these u's. That works, but today we're really going to focus on a second method using a substitution and undetermined coefficients. At the top here, we spent a significant amount of time in 4.3 solving for a characteristic equation. When we had constant coefficients out in front of a second order differential equation, and this was for the homogeneous one where 0 was on the right, we assumed that e to the mx would be a solution, and we'd substitute that in, we'd get a quadratic, we could come up with these nice general solutions. Now, just a couple of days ago, we were working with the Cauchy-Euler, and we were seeing that we would assume that x to the m would be a solution. And they're definitely strong comparisons when you're looking at 4.3 and 4.7. Today we're going to take that a little bit further. We're going to say, what if you have a Cauchy-Euler? Might you be able to make it look more like what we saw in 4.3? And indeed we can. We're going to do that right now. So for method 2, here's the key. We're going to say, look, x is going to be of the form, make a substitution of e to the t. Now, if you took a natural log of both sides, you'd have the ln of x equals the ln of e to the t. That quickly would lead you to this, that t would equal the ln of x. And, right now we're well on our way to being able to go through this. For part B, they're asking us to do something here. Y prime would equal something. So, tell you what, y prime is really dy dx, isn't it? And, right now it sure looks like our y is in fact a function of x, but now we're seeing t's throw in. So we could write this via the chain rule as dy dt times, if y was a function of t but t is a function of x, take your derivative of the inside and then you'd have dt dx. Well, I just want to point this off to the side here. If t is equal to the ln of x, what is dt dx, assuming that we've made this substitution? Well, dt dx, you could see very quickly, would just be 1 over x. And that's what we're going to substitute in right here. So dy dx is dy dt, dt dx is 1 over x, and we can even move that 1 over x out in front. And hey, look at that right now. This is how we went about finding what y prime is. So that's well and good. We have a second order differential equation with a y prime or a dy dx. We can, change this now. What about y double prime? What about taking another derivative here? Let's do that. As I take a second derivative, you can see right here we're going to need the product rule. So I'm going to take my first function, 1 over x, but then I'm going to take my derivative of dy dt. Well, it's really tempting to stop right here and say, there it is, I've taken my derivative. But remember, you just took your derivative with respect to x. And t is a function of x. So this is the chain rule. You have to take the derivative of the inside, and that's your dt dx. Then, this is kind of like our u v prime. Now we're going to take our derivative of 1 over x, one of the most famous derivatives in calculus. You'd get negative 1 over x squared times your dy dt. But here we go again. dt dx right here is 1 over x. So I'm going to write this as 1 over x times, here's our second derivative of y with respect to t. Here's your 1 over x. And this I'm just going to write as minus 1 over x squared dy dt. But I do want to point out to you that both of these terms have a 1 over x squared in them. That first term, you've got a 1 over x and a 1 over x. That's going to multiply to 1 over x squared. So I hope it's not too much of a stretch to just say, let's factor out a 1 over x squared. And the big question is, what will you be left with? Well, your first term is just the second derivative of y with respect to t. And I would say minus dy dt. And guys, that right there is another form of your second derivative. And I guess what I'm really getting at is that's what we're seeing right up here in our list. That's letter B. You can see we just proved that. So once you have a form of y prime and y double prime, substitute that in. By the way, simultaneously in green, you could make substitutions. Wherever you have an x, perhaps on the right-hand side, if it's non-homogeneous, you can change that into e to the t and so forth. But get everything in terms of just a y and a t. Solve for your characteristic equation much the same way you've been doing. It's now going to look like you're in 4.3. That's the benefit of doing this method. You'll see in just a moment. Then we'll go to E, find the particular solution with undetermined coefficients. That's where we looked up in a table and we were able to get some help. Finally, for F, we have to realize that our original problem didn't have t's in them. We'll have to re-substitute to get your equation in just x and y. Just in case you have a third derivative, this is the formula that you would see. You are encouraged to try to derive this on your own. By the way, on that far left-hand edge, you can see that's what we were doing. We had derived and proved the second derivative with respect to y. You're encouraged to do that just as well. So we're just going to do one problem right now. And this is what you can see. You can see it's a non-homogeneous Cauchy-Euler differential equation. Look, in front of y double prime, you have x to the second. In front of the first derivative, y prime, you have x to the first. And you get the idea. Even with y right there, that's a zero derivative. You've got x to the zero out in front. But how can we proceed? Well, we can proceed this way in this new lesson here. We're going to say, look, wherever we have an x, we're going to substitute in an e to the t power. If you took an ln on both sides, you could see that you'd have ln of x would equal t. But like we just proved a moment ago, and this was on that list that we saw, we had y prime was 1 over x dy dt. We had y double prime was 1 over x squared. And then we had our second derivative of y with respect to t minus our first derivative with respect to t. So these four items right here are the critical link. And right now we're going to make these substitutions. So look, I'll have x squared out in front, but for y double prime, I'm going to have this 1 over x squared, second derivative of y with respect to t, minus dy dt. That'll say minus 3x, but for y prime, I'll have 1 over x dy dt. For 13, well, we'll just say it's 13y. I don't have anything to substitute there. Please watch out. I think this maybe is the issue where kids can really get into trouble. I think we get so focused on the left-hand side that sometimes we forget that substitutions have to be applied on the right-hand side as well. And, you know, that x is really e to the t. And right now you can see this is your new form. Now, you can see in the Cauchy-Euler situation, this x squared and this x squared are gone. This x and this x are gone. So all of a sudden, things get cleaned up, and it's looking so much like section 4.3 right now. You know, if you're looking at this brand new differential equation, once you get all this canceling, everything's canceled out. If you just started with this problem right here, you'd say, well, this doesn't look like a Cauchy-Euler. It looks like something that we were working with way long ago. And indeed it does. That's the benefit. It's turning this problem into something that looks way more familiar. Here's a -1 and -3. That's a -4 dy dt. And we have a 13y equals 4 plus e to the t. Now, at this point, you know, you want to be able to solve the characteristic equation, make that substitution. You're more or less assuming that y equals e to the mt. You will get what we have seen so very often. And again, we're assuming that, you know, this is for homogeneous. This is for y sub c, the characteristic. You're assuming that you got 0 on the right-hand side. To speed this up, guys, we could certainly use the quadratic formula, or because you have a TI-89, you could do C-solve, typing in this equation, comma, with that variable. I'll leave it to you to confirm very fast that this is really what you're going to wind up with. And it's not hard to get that, and you're more than welcome to solve this by hand as well. But, you know, this is going back to something that we had done for the sake of brevity and being able to finish up this video quickly. There's your characteristic equation. But then what? We could say, well, now with undetermined coefficients, we're looking at this right-hand side. And the right-hand side here would fit a table solution that we'd seen. We might say, well, there's a 4, that's a constant, and we've got a 1 out in front of e to the t, so we could say b e to the t. Let's take a derivative. The derivative of a goes away. You'd have b e to the t. Second derivative, well, you can see what's happening with this e to the t. That's pretty much where we're going. And now we're going to recopy this differential equation by substituting in, like for the second derivative, we'll have b e to the t minus 4 times the first derivative. That's b e to the t plus 13 times y. Well, now we'll have our a plus b e to the t. And then our right-hand side, well, we'll have a 4 plus e to the t. And let's just go ahead and get this thing cleaned up real quick. Looks like we're going to run out of time. You know, with this video, we're going to have to pick back up. But you can see we're well on our way to getting this where we need to go. And you know what? Forgive me, I miscopied. That's a 3 e to the t over there. I had miscopied that original problem, didn't I? Got to be real careful there. So sorry about that. We're going to pick back up with this video in just a moment.